Hi guys, I want to go quickly over the homework from, so this is the homework from, it's 3.2, right? 3.2 on growth of functions. I'll just say big O. And I don't want to spend too much time on it. I want you to understand how to calculate the big O of functions. So I want to go over a couple of things and also understand what is the order of magnitude. And so the first question, that was number 22. There were a lot of functions there. We had radical of n, we had 1000 log n. Okay, let me write them down as in order of magnitude. Okay, so let's put radical n. Radical n is not a fast-growing function. Now you might say, how do I know? Well, it is of course n to the power a half, and so we mostly dealt with functions that are of degree polynomials, so they have a natural number as a degree, but they could have rational degrees, and the same thing. If you have a polynomial with rational degrees, or if you have an expression with rational degrees, the highest one will be the dominant term. Same as with whole numbers. Okay, so that's there. Then the next one is 1000 log n. Where does that is sit? Okay, that might not be. We know from the chart that I showed you last time. You know that the log of n is smaller than n. So let me record this fact here. But how does it stand vis-a-vis n to the power a half? Well, it's more than that. Log of n is less than n to any power, of course, except for the positive powers. So the log of n is really slower than any power of n, even rational power. So now it's not log of n, it's 1000 log of n. Does that make a difference? No, we know that these constant factors have no effect on the complexity. 1000 log n has the same complexity. Has no effect on the big O. It has the same big O as log of n. Okay, the next one was n log n. Now we see here. So let me go back to what I had here. So that the log of n is less than n. So that means that n of log of n is less than n squared if I multiply both sides with n squared. So n of log n will be less than n squared, but of course it will be bigger than n. Okay, so we have n here. So I'm going to put it somewhere here, n log of n. The next one that we have to put in is 2n factorial. Now we know that factorials are extremely fast. So remember that 2n factorial is the same as n factorial, and that is order n to the power n. This is not just a fixed power, this is a variable power, and they go all the way on top. So here is 2n factorial. Then we have 2 to the power n. That's an exponential function, and we know that exponential functions, so let me write it here a little bit more general. If you n to any rational degree, so I'll write n to the q, that is always in O. When I write less than, I mean as in growth rate. In growth rate, n to the power, sorry, let me rewrite this. N to the power q, where q could be any number, positive number, so q is 0, but it could be a rational number, is always bigger than the log of n. That's that I just said. But it is also smaller than any exponential function, a to the base n, where a is an exponential function with base bigger than 1. In other words, exponential growth. Okay, so we have now 2 to the n. So 2 to the n is going to be bigger than any power of n, and of course therefore also bigger than n of these n log n's, because n log n is smaller than n squared. So they have to go on top. But there are two powers, 2 to the n and 3 to the n, and then of course is the bigger the base, the bigger the function. So 3 to the n will be higher up than 2 to the n. Now I might be running out of a bit of space, so what else is there? And then is n squared divided by a million. Now divided by a million makes it of course extremely small. Well, yeah, if n is 1000, that is no longer small, because so we are talking here about n squared over a million, right? Let me write it up. That is small if n is 1, but if it's n 1000, then it's already 1. And if n is 10,000, we are already talking about 100 and so on. So it's not really small for big n. Where does it go? Well, we know this is O of n squared. So Because why? Because any constant, and this is the, what's the constant here? 1 over a million times n squared, right? You can think of this as the constant. So we can ignore that constant. So where does n squared go? Well, that's why I drew this picture here. So n squared goes there. So I have to move this a little bit. So let me move this guy. I'll move it down here a little bit. And then the other one is n squared. Or n squared divided by a million. That was actually the one that they proposed. And okay, that's it. So this is of course from smallest to biggest. I wrote it in that order. Okay, I hope that was okay. And then the other one was 26. There were a couple of functions that you had to then analyze what big O they were. So let me do 26a. That is n cubed plus n squared log n times log n plus 1 plus 17 log n plus 19 times n cubed plus 2. Okay, so how do you do this? Well, we have two rules. We have a sum rule and have a product rule, right? So let me remind them here. I'll write them over here. So if you have to do the O of f plus g, that is the maximum of OF and OG. You find whatever is the biggest. And if you have to do the product, then you just multiply. Okay. So in other words, we're gonna, if you can think of O as simplifying the expression without losing the growth rate. So let's think about it that way. Okay. So what is then this first factor here? Well, we have a sum there. So we should look at what is the O of this, that is n cubed. What is the O of that? Well, is that bigger or less? Remember, we have this log n less than n. So if I multiply both sides, let's do it here with an n squared. So if I put here n squared and then here n squared times n squared, this is n cubed. So you see that n squared log n is actually smaller, really smaller here than n cubed. So what is the biggest one? So using the max rule here, this is n cubed. Okay, so I should actually say it's the O of n cubed. So I'm gonna put the O all the way in the front that I don't have to repeat each time that I'm talking about O's here. So this one simplifies to n cubed. How does this one simplify? Well, it's again a sum, and we have two functions, log of n, and the constant. Now we know that the constant is all the way in the bottom. It's the smallest of all functions because it doesn't grow at all. In fact, it doesn't even become infinite, where all these other functions all go to infinity if n is infinite. So again, what is the biggest one is the log of n. Okay, now this is a product, and therefore this is just n cubed log of n. Right. So in principle, I said I didn't write it, but there's an O log n and there's an O n cubed. But even taking this together, this is the O of n cubed log n. Let me not write the logs the O's anymore. Well, here we have in the same as in the last factor here, we have a logarithm with a constant, but the constant in front of it, remember, never matters. And so this is O of log n. So let me write that. So this is O of log n. This is O of a constant, O of 1. That's how one writes that. And so the maximum of these two is O of log n. I didn't write it up here in the previous case, but that's the same analysis, right? Okay, so O of log n. And what is the O of this guy? Well, it's a sum, but we know now by polynomials it's really the highest degree. So that is n cubed. And therefore, this is a product. So to calculate the product, we have the product rule, just multiply. So it's n cubed log of n. Right, I said I'm not going to write the O's anymore, so let me get rid of these O's here. I hope that that is clear what I'm writing here. Perhaps this is a bit weird if I write just in one here. Okay. Okay, and then finally we have to talk about this plus still. That's how we put everything finally together, right? So let's put this in a different color. So this is how we put everything. That's not a different color. This is how we put everything together. It's a plus. That means we have to take the max, but you're the same. So the conclusion is this is O n cubed log of n. Okay, that was for A. The other two are a little bit more. Okay, no, let's do the other one. The B, 26b, 2 to the n plus n squared times n cubed plus 3 to the n. Okay, what's the big O? Well, we have to analyze this. This is a, let's do this. This is a sum. So we have to find the O of this, which is 2 to the n. What is the O of that? That is n squared. Right? So again, I'm not writing the O anymore. What do we do with the plus? We have to take the maximum. And the maximum here, of course, is 2 to the n. So we see that this whole thing is O of 2 to the n. Now, what happens here, it's kind of very similar, because this is again a polynomial here, so this will be O of n cubed, and this will be 3 to the n. Now, it's not because this is written first that this is the maximum, right? No, the maximum is this one, because exponentials grow much faster than polynomials. That is a fact that people have stated several times already, probably in your career, that exponential growth exceeds any polynomial growth, which is bad news, as people always say, because population growth is exponential, whereas increase in productivity and manufacturing and economy growth is all a polynomial. So eventually the number of people will outgrow the function is an exponential, right? If this is an exponential and this is the production, at some point this production curve is going to go below the population curve. I mean, production per capita, let's say. And at this point, we are going to starve. Not a good thing. Okay. So what is the biggest one here, therefore, is 3 to the n. And now what do we do with this? Well, okay, we put them together again. But what is this? This is a multiplication. So for the multiplication, we have the multiplication rule. Just multiply them. So 2 to the n times 3 to the n. And if you want to write this as one single exponential, what kind of what one normally does if one wants to give an O. The O, you remember, if you write O of something, this should always be as simple as possible. So this is 6 to the n. I hope you see this. It's not 5 to the n. I hope that you see that. It's 6 to the n, right? It's 2 times 3 to the power n. Okay, and then finally C. C is perhaps a little bit over the edge, over the top. N to the n plus n 2 to the n plus 5 to the power n, and then times n factorial plus 5 to the n. Now, I already argued in the previous case here, we put n factorial here, which itself is less than n to the n. N factorial is grows not as fast as n to the n, but that's the best, simplest expression that we can find to analyze n factorial. Now, n factorial, we say it's a simple expression because it's an n with a factorial after, but the calculation of n factorial is a very difficult process. To calculate n factorial, you have to calculate the product of n and n minus 1 and so on and so on and so on. That's a lot of calculations where n to the n is just one single exponent. Exponential, one single power that you have to calculate. Okay, so n to the n, so we have to know this is a sum again, the first factor. So again, it's first a sum, right? That we have to first analyze this. This is a sum, so we have to know the complexities. This is, the growth of grade. This is n to the n. Now, what is this one? Well, this is what it is. It's really, I cannot simplify this. So why is this? Well, remember, 1 is less than n, because 1 is less than everything. So if I multiply now both sides with 2 to the n, then I get 2 to the n is less than n times 2 to the n. So putting an extra n after an exponential makes it even bigger than this exponential. Okay, so this is bigger than 2 to the n. What about this one, that is 5 to the n? So where does that lie? Okay, now things get a little bit tricky, right? How does 5 to the n compare to n times 2 to the n? Well, 5 to the n is bigger. Now this might not be clear at all, but in some cases it doesn't matter which one is the biggest of these two, because this is really much bigger. Now you say, okay, why? Could this n not screw up things a little bit? I understand that n to the n is bigger than 2 to the n, but why is n times 2 to the n bigger? Well, okay. So let's factor out an n here, then we get this, n minus 1, and factor out the 2 there, 2n minus 1. Okay? So now, n to the n minus 1 is less than 2 to the n minus 1. I hope that is clear, because here we have, they're both the same power, but this is sorry, I said it right and I wrote it wrong. Sorry, no, I don't know what I said. Of course, I mean the opposite rate, right? So I mean 2 to the n minus 1 is less than n to the n minus 1. Why? Because the powers are the same, but this is a base 2, this is fixed base, this base is going to get bigger. So this is clearly the dominant one. Now, okay, so now multiply both sides with n. So I get n to the n minus 1 is less than n times n to the n minus 1, which is n to the n. So you see already that this guy is less than this guy. But you say, oh, but it was 2 to the n. Yeah, but that's just a factor 2. That doesn't make any difference. And so this is n to the 2 to the n. And therefore it's much smaller, in fact. So really the biggest one is this one. So this is the biggest one. So this is n to the n. And here, well, n factorial, we have seen, is bigger than any exponential. And therefore this is n factorial. But we don't have a good estimate for n factorial. We have to write this as n to the n. This is 5 to the n. So again, the maximum here is n to the n. And we see n to the n here, n to the n here. Now what do you have to do? Well, we multiply them. So we get n to the n times n to the n, which is n to the 2n. Now these are functions that we never will run into, so I don't want to spend too much time on it, but I guess some of you might still want to know what happens with these two. Suppose we had to figure out what these two are. Well, let's write it down here. Let's think that it is bigger. Then we would have this, right? Now let's divide both sides by 2. That means that n would be bigger than 5 to the n divided by 2 to the n. But that is just 5 halves to the power n. But wait a second. This is an exponential with base bigger than 1. So it's exponential growth. Therefore, it is much bigger than n. So this is the wrong inequality. So the right inequality would be the other way around. Let's do that. So let's change the inequality and say, no. The right inequality is this is bigger, so n is much smaller, and therefore this is smaller. Because it comes from the same equation, right? It's just now multiply both sides with 2 to the n. But whereas this and this is important, this is not going to be important for us. So don't dwell too long on the third one, but on the first two, make sure that you understand the difference between polynomial growth and exponential growth. That is going to be very important in, you saw that in today's lecture.